So let's write this one down, this idea number 4. We're going to impute based on the distribution, not just the mean, of observed values for this variable. And the motivation is that when I filled in the mean everywhere, I was way underestimating the variance of the variable. So what I just showed you on the slides was the non-parametric approach. And that is when we draw with replacement from the observed values. Now, let me say that I have actually done this on real studies. Sometimes it's still quick and dirty, you know, like filling in the means. It's just a way to get to the next step. I'm not claiming these guesses are right, but it's a way to avoid dropping values from the data set and fill in values that are dispersed in a somewhat reasonable way. If there are not too many of them, this can be a reasonable thing to do. What about the parametric version of this? Here's the idea. When you look at the observed data, like maybe you make a histogram of all the education values that you did observe, maybe they look like a famous distribution. Like maybe they look normal, or maybe you realize that they're binomial, or they're exponential, if you've seen something like that, a very skewed distribution. But basically, if you look at a histogram of the education values that you did observe, and they look like a famous distribution, right? Like they look, let's kind of draw a famous distribution here. Suppose that it looks kind of normal, right? So the non-parametric approach is, okay, let's just stick our hand into this histogram and, oop, I drew this value, and let's use that, right? But the parametric version says, hey, you know what? Let's approximate this histogram with a normal curve. Let's estimate its mean and its standard deviation. And then instead of drawing from the data values I actually observed, let me draw from a normal distribution that has the same mean and variance as the data that I actually observed. So I'm going to say, using observed values, estimate the parameters of some appropriate famous distribution, some famous distribution that you feel the data seems to follow. And draw from that distribution. So just comparing the non-parametric and parametric versions to each other, notice that in the non-parametric version, it's only possible to draw values that were actually observed in your data set. So suppose that in your data set for the education values, you have 5, and you have a couple of 6s, and somebody has an 8, and a 10, and a 13, and a 17. Suppose that's your data set. If you have the non-parametric version of imputing based on the distribution, you know, you might draw an 8 for somebody, or a 5 for somebody, right? And that's fine. That's appropriate. But it's actually not possible to draw a 12, even though you can see that 12 was very, very likely a possible number of years of education somebody could have. If it wasn't literally observed in the data set, then you have 0 chance of selecting it. So that's a drawback of the non-parametric that is fixed by the parametric. So if I fit a normal curve to these, and instead of drawing from exactly these values, I draw from some normal curve that has, you know, the mean equal to the mean of these and variance equal to the sample variance of these, and I draw, now all of a sudden I can get a 12, right? I can get a 16, so this is good. The thing is, though, I can also get a 5.972, which may not be very realistic. So there's this trade-off, and you have to decide what's appropriate in any particular data set. Would you rather restrict yourself to drawing from the values you actually observed, or would you rather draw from some distribution that's going to allow you to have values that are not in the data set? Maybe those values not in the data set are desirable, and maybe they're not. So what else do we want to say about this one? Well, this maintains the observed mean and variance. This time, mean and variance of the observed values, right? So one thing that's important to note about this method is that there's some randomness to it. So if you and a friend each use this approach, you will end up imputing different values for the same person. That's okay. It's why you need a seed when you are drawing random values, but it's just something to note. This method works pretty well if you have missing completely at random, because it maintains the mean and variance, the observed values, which are fine if you just have a random subset of the data. Not so good if you have missing at random or missing not at random, because then you'll be filling in values such that the data looks like the observed distribution, which is a biased distribution if you are missing the data in a systematically biased way. Now remember, again, you don't know whether you have missing completely at random or missing at random or missing not at random, but this will generally work if it's missing completely at random. Now, so we went from imputing the mean. So we started with filling in missingness as a category. I like that idea. Then we talked about dropping missing values. We said that's not ideal because really we should be trying to fill them in with something. Then we tried filling them in with the mean, and that was okay, sort of. We maintained the observed mean, but we didn't maintain the variance, right? So now we have this idea that we're describing on this slide, which maintains the variance. But what we didn't maintain this time with imputing based on the distribution of the observed values for this variable was the relationship between the variables. Right? We're not taking advantage of the fact that we do know age, and age is correlated with education for our example. So the next idea that we're going to talk about is imputing based on the observed values of other variables. Right? And now, at this moment, we're starting to get into methods that people realistically frequently use. Okay, the other ones have pretty big drawbacks, but now we're starting to get into methods that are more common when people are trying to do a good job handling missing data. So once again, there's going to be non-parametric and parametric ideas here. So in terms of the non-parametric, we can create a subset of units that are similar based on some other variable. So for example, maybe we find a bunch of people who are in the same age group, right? We put people in age categories. And then we draw with replacement from these units. And I'll show you this when we go back to the slides in a moment. So when we know that age and education are correlated, I can split people up into age groups. And then if someone is missing education, I can randomly draw the education of someone from their same age group. Okay, that's the idea. I'm going to split people up into buckets so that I fill in your education not with a random draw from the entire data set, but with a random draw from people who are like you in some way that I have defined ahead of time. That's the non-parametric version. The parametric version of the same thing is something like a regression. So you can create a parametric model like a linear regression. Connecting the variable that has missingness to other variables. And then use the model to impute. So for example, suppose that I have an X value and then a Y value. Here's the data where I observe both. Here's a linear regression line that I fit to them. Let me make it look a little more like the right linear regression line. So now, if it turns out that for a person with this value of X, I'm missing Y, well, okay, I should draw a value from this normal distribution, right? The normal distribution centered at the line with variance equal to the residual variance. And so I might, for example, end up like right here. And this would be my imputed Y value, right? That's the parametric version. So the non-parametric, I'll show you on a slide in a moment. Parametric version, something like I'm running a linear regression. So what do we want to say about this method? It works if missing completely at random, and the more relationships between variables you can take into account, the more useful this will be. It also is the first method we're saying this works if it's missing at random. That's something like the Chinese high school student problem. The method that I showed you for the Chinese high school student problem was, you could think of as a non-parametric version of this number 5 strategy, right? If somebody was from China, then I imputed the number of kids in their family with what I observed for the other people from China, which was 1 child. Okay, so this works if missing at random, if you specify the correct relationship between variables. So we said missing at random is when the fact that one variable is missing is correlated with some other variable. You have to figure out what that variable is, right? So this method works if you're imputing based on some other variable, and that's the right variable to be imputing on. And of course, you never know if that's true, but you can try hard. And this method does not work if missing at not at random. In fact, nothing works if it's missing not at random.